Excellent. Well, I'd like to start off today by welcoming everybody to another Clippard webinar. Today, joining me is going to be Mr. Doug Painter, and Doug is the product manager for all the proportional valve products at Clippard, and he's going to talk about the Eclipse. The Eclipse, a phenomenal product from Clippard, patented, and has a lot of really cool features that we'll dive into in a moment. Also, Tom Seville is with us for the Q&A section today, and Tom was the lead engineer on this project, who also had the patent in his name there. So we're happy to have Tom joining us today. And as we go through a couple ground rule questions here, everybody's just in on a listening mode, but at any time you have any issues, throw them into the chat. And then towards the end, if you've got questions, type them into the question box and we'll address all those at the end. So with that, I'll hand it off to Doug, and Doug will begin presenting on a presentation with lots of pretty graphics and videos and such. So Doug, it's all yours.
So is everybody able to see my screen? I just want to make sure that everybody can see the presentation. Obviously, when we're doing things live, anything's possible. So I just wanted to make sure that we're good to go. What I'm going to do is I'm going to go stop. I apologize for that, but what I wanted to go over, and first of all, thanks a lot, Rob, for introducing me. I am the product manager for the Eclipse. I will be doing the overview for the Eclipse product line, kind of basically not doing a real deep dive, but going over the things that we want you to walk away from. Let me get rid of this here as well. All right, so the overview, the Eclipse, what is it? How does it go together? Patented technology, how unique is it? What makes it special? The markets, we're going to discuss the markets that we're actually having some success with, but also those markets where we feel that the addition of a product like the Eclipse will be a benefit to the end results of your applications. So what is it? It's a patented stepper-controlled two-way valve that is proportional isolation. I'm very excited about that, simply because when I start searching the web for proportional isolation valves, there's very few products out there that actually can bring to the table what the Eclipse does. Some of the key features: ceramic sliding seal. I have two plates internally that we've done a lot of engineering design work on, that in the surface finishes, that by simply marrying the two parts together, you're able to create a seal. The nice finish on those two surfaces creates a nice little bonding seal. It is capable of handling liquid and gas. All the parts are all the wetted parts are inert. So because I'm working with ceramics, pretty much you can run just about anything through there. We will touch on a few of the medias that we don't want to work with. Zero dead volume, and what we mean by dead volume is any area where the media that you're controlling, whether it's fluid or gas, can find a place to hold and stay and contaminate the next step function. Basically, we have a fully flushable flow path inside the Eclipse. The internal volume of the Eclipse is 9/10 thousandths of a cubic inch, very small. If anyone needs a little bit more detail on the internal area, we can certainly accommodate that. And then also one of the nice features about this is that it's bidirectional. Pressure to A or B port of this valve is fine. We have a pressure range of full vacuum to 30 psi. As long as you're within that range, you have no problem with whatever port you want to work with. It's patented technology. We're here at Clippard. It's been a while since Clippard has found a product worth dedicating the tremendous amount of engineering time, resources, money into a product that we feel is going to be a big hit in the medical and life science world. Tom Seville and his engineering team has done a great job in the development of this, and we're very proud that we've been able to put a product in and have it patented. So how does it work? There are three main components to the Eclipse. The first would be the ceramic plates. The machining that we do, the molding, a tremendous amount of engineering work has gone into the development of these flow paths. And so we have an upper plate or the slide mechanism, and then a base plate. And so the surface finish that we were able to, the lap surface finish that we have on the two plates allows us, as those plates start to slide across each other, to develop a very linear flow control about the movement. And basically the movement is going to be created by the stepper motor. Stepper motor is now in contact with the carrier assembly, which will hold the upper slide ceramic plate and slide it across the base plate. And so all these components go together, but even though I'm able to put the two ceramic surfaces together and create a seal, I still need to utilize the compression springs to hold everything together. Again, we're working from anywhere from full vacuum to 30 PSI through the Eclipse. Here's a short little video of basically how the Eclipse goes together. As you can see, we have the two ceramic plates. The base plate will be sit in and fitted in, and then the stepper motor will come in and actually attach to the carrier assembly. That carrier assembly, or what the nut would be actually holding the upper slide, and then we'll hold the compression springs in there and have a nice little fit into the overall housing. So what's happening inside? We have a product that's called the ScpV, and it's been difficult because that is a stepper-driven needle valve. In this case, this is a stepper-driven variable aperture valve. Basically, I am varying the size of an orifice based on these sliding seals. As you can see on the isometric view to the left, we've got the actual plates are in the home position, fully closed. And as I said, you could use A or B port as your supply, but in this case, yellow is going to be our supply. Now and as I go into the overview on number one, it's the same picture as the isometric view to the left, but now I moved into number two, and I'm starting to give the motor a command. I'm actually starting to step out and move. And the great thing about our flow paths, they have rounded ends. And so as I'm transitioning across the plate, the two rounded edges start to overlap or eclipse. And so now I'm able to, in a nonlinear fashion, vary the delivery of the gas or the fluid into the circuit or downstream control environment. That's a nice little soft start option. And as we get further into this, you'll see that you're able to control the rate of that soft start. As we move further and further into the rectangular section of the flow path, we get into a more linear flow control of the output flow until the point where we get to a fully open position. So the Eclipse stepper motor, basically, it's a bipolar hybrid stepper motor. It's kind of like a DC brushless DC motor, but instead of actually continually rotating, it's divided. The revolution is divided into an equal number of discrete steps. This motor that we have is actually capable of doing 200 steps per revolution. We chose the Hayden-Kirk size NEMA 8, and this motor gives us a 1.8 degree step angle. And by going this route, we're able to provide 600 thousandths of an inch position change per step. Now that's in the full mode, and we'll get into what we can do micro-stepping wise, but in a full mode step or full step mode, we're going to be able to provide each step of 600 thousandths of an inch incremental change. As you can see to the right, the way the motor works is all I'm doing is I'm energizing, de-energizing magnets to create a rotation internally to the point where I'm able to make these types of position changes of 600 thousandths or better. To make this Eclipse work, I need to have two components. I need to have a bipolar chopper driver. Our ScpV-D-1 is something that we offer as a convenience. It's going to take the signal and chop the information to the motor, and but I need to be able to give the motor a command, so I need the PLC as well. I'm pulse width modulating 0.5 volt signal, and I'm going to need to have both of these to make it work. But we offer this as a convenience, the bipolar chopper driver, simply because we know that you want to get the Eclipse, you want to do the testing, but this is something we know that you're going to design into your application. Typically, it's a heck of a lot less of a cost for you if you just design your own chopper driver when you're putting this into equipment that you're going to produce. So what makes the Eclipse unique? The 4 things we'll talk about. The first one's soft start. Second one would be resolution. Third would be the flow path, and fourth would be the ceramics. The soft start, I have a lot of familiarity with what goes on because of the different products that we manufacture. Here we have a straight line that we need to follow, and we manufacture 2 other products, the EVP and the DVP proportional solenoid valves. And when I'm working with those type of valves, I can get very good control. The more current that I apply to the valve, the more of an output flow I can control. But because of the dynamics of that product, I'm putting current to the solenoid. I'm generating enough current inside so that I can have enough magnetic pull to pull my spring mechanism or my seal mechanism off the nozzle. When I do that, in a lot of cases, in a lot of sensitive applications, that jump or that initial momentum off of the nozzle creates some type of jump in your pressure or in your flow. And in a lot of applications, that's just not, you can't have that. So I'm very familiar with this section of the control of a proportional solenoid valve, and the soft start for the Eclipse. Well, it really actually, because of the rounded edges of our flow paths, as you can see, we're actually overlapping, and we're truly eclipsing that flow path. We're able to vary that flow path at what rate you want to go with, and then immediately it automatically gives you a very soft start, a soft introduction into the system downstream. So next, we're going to talk about the UltraFine Resolution. I've already told you that the 1.8 degree step angle allows for each step to be 600 thousandths of an inch incremental position change in full step mode. But now we need to talk about that we can actually micro step this. So I'm in full step, but I can micro step this down from full step to half step to quarter step, 8th step, and then a 16th step. And by going to the 16th step, we're able to tell you about this ungodly number of 3.75 millionths of an inch controllable. Well, I put it in a different perspective for you. When we're microstepping, the Eclipse has an effective orifice of 20 thousandths, and I'm giving you in a full step 1,125 steps to modulate that 20 thousandths orifice. I go into a 16th step, and I'm modulating, or I'm varying the effective orifice of 20 thousandths, but now I'm giving you 18,000 steps to modulate that orifice. That is some very fine, ultra-fine resolution. The flow path, we talked about this. A lot of effort went into this. We have a lot of experience with dead volume, or no dead volume, or fully flushable. Simply because we have another product line, the isolation series, the NR series, and the pinch valves. By having that and manufacturing that and dealing with applications where dead volume or sharp corners are definitely an issue for applications, we take that knowledge and we move it into the design of the Eclipse ceramic flow pathways. So there is no dead volume. There's fully flushable. The sharp corners, we realize that in a lot of delicate applications, sharp corners or turns are detrimental to the actual sample that you're trying to pass. The object of the game is to control the flow as smoothly as possible. We even come in with the soft start so that you're able to eclipse and change the rate that you're able to introduce the fluid. Again, we we can do the micro stepping on that flow path. And so you can micro step the soft start aspect of it as you eclipse to really get a fine control of how you're delivering to your system. Next is ceramics. First of all, it is ceramic, and it's an inert material, so it can work with a tremendous amount of different gases and fluids. The amount of time and effort went into figuring out how the precision molding and the geometry of the flow paths is basically what makes this a very smooth product for you. The lap surface finish, we're sliding across the surface, so obviously that's going to be a concern, when we're working with different fluids. What kind of life can we get out of this? And so a lot of time and effort, a lot of design work went into figuring out the right makeup of the ceramic plates. Here's a little video that's going to cover just some basic operations of the Eclipse. I think, Rachel, are you going to put that on? I don't have access to that video. Guess not.
Here at Clippard, we've created this really cool demo. It's a user-friendly type of demo for our Eclipse, and it basically utilizes our driver board, our regulator, and the Eclipse, and a nice touchscreen. I start in full mode with 30 psi as my supply, and all I'm really doing is I'm just generating a curve from fully closed to fully open in the different microstep modes. As you can see, on the demo, the demo automatically rescales the graph to accommodate which microstep function I'm in. A nice function of this demo allows the user to record multiple graphs on the same screen for comparison purposes. I can change any parameters, and as long as I actuate the repeat tab on the display, all prior curves stay displayed for comparison. It's a nice little option for you to work at when you're changing the parameters. You want to see how the performance curves marry up from one curve to the next. As I finish this segment in that 16th microstep mode, you can see it takes a bit of time to get through the 18,000 steps. I would have preferred to speed this up to 6,000 steps per second, but unfortunately the demo only allows for the speed to be increased to 2,000 steps per second. Our next set of performance curves is simply to command the Eclipse to go to fully open and back to fully closed. Very simple operation, but I'm using half-step microstepping mode. And the only difference with these curves, as you can see the performance happening here, is that I'm making incremental changes to the supply pressure in 5 psi increments. Here's that, I'm changing my supply pressure, and basically I'm doing the repeat function as I did before, and I'm recording all the different performance curves right there for you to do your comparison to. Again, all I'm doing is hitting the repeat tab and keeping all my curves readily available there.
So can everybody hear me? All right. So what are the applications? We're going to go into, as I said before, we're going to go into the area. Let's see here. I'm sorry? Are we good? All right. Sorry about that, guys, but this is live. All right. So we'll get into these applications where we've had some success. And also applications where we have been working with other products and we're able to transition them from those products into the Eclipse. And then also the applications where we feel that the Eclipse is definitely going to be a benefit to your end results. The first one I want to talk about is caustic gas flow control. So you can see to the right, I've got a list of different types of gases or fluids that we don't really want to work with. You know, that I don't want to work with those, but that doesn't mean that we can't work with that in your application. Maybe the amount of these types of medias are very, very low percentages. We're going to need to have a conversation about it to make sure that we all are on the same page about what you're passing through with the ceramics, if some of these types of fluids are being utilized in your application. However, let's look at ammonia. I don't know how many of you have worked with ammonia and how difficult it is to work with that. I've done a lot of work with it where we try to get our solenoid, our EVP and DVP valves set up so that we can proportionally control the delivery of ammonia. The problem with that is I have so many different materials that I have to keep in mind for compatibility, and so the seals or the finish on the stainless steel. What kind of stainless steel am I working with? There's just a tremendous amount of things that go into the working with ammonia process. It is just takes a lot of time and a lot of headache. Right out of the gate, as a standard component, the Eclipse can work with ammonia, no problem whatsoever. And you know, applications that are like gas chromatography, where they do the delivery of ammonia in some applications. This is a great product for that. Ultra low controllable range. I mean, you know, look at these different companies that we have worked with. I've done a lot of work with DNA sequencing, gas chromatography, flow cytometry. But basically, I've talked to you about the microstepping. And the full step, we're generating each step 600 thousandths of an inch incremental position change. And now we were able to microstep it down to the 3.75 millionths of an inch, or give you the ability to vary 20 thousandths orifice, but 18,000 times. So what do you need in the application? What kind of delivery do you need of the fluids? Do you need to deliver it? Do you need to draw it? It's up to you, but let us know what you need. The power settings. So we didn't talk about this, but basically the stepper motor is, you know, you're energizing, de-energizing to get movement out of or to energize the magnets inside the motor to get movement or rotation. And with the stepper motor, all you have to do is remove power and it'll hold last in position. So in applications where you want to get to a particular flow rate, remove power and just leave it alone, you're not building up heat, causing any issues with the heat, or having needless power to hold a position or to maintain a flow rate. This is an ideal thing for those type of applications. High precision fluid proportional valve. So let's be honest. The Eclipse, as great as it is, a variable aperture valve, it's an isolation valve, it's proportional, it's phenomenal. It'll provide you all kinds of resolution. But if you don't have a differential of some sort, then what good is it? You have to be able to drive something through or draw it through. And one of the products that we've manufactured, the Cordis product, it's a nice electronic pressure regulator. It utilizes our manufactured EVP and DVP valves so that we're able to smoothly control pressure on the head pressure of maybe some fluid that you want to push through the system. It doesn't, and you could utilize the electronic regulator to push it, or you could use the electronic regulator to pull it. Variable vacuum, right? I can draw through or push through. Good application would be 3D bioprinting, extrusion printing. I'm pushing a fluid through. I'm using the Eclipse to actually control the rate that I'm feeding this fluid out. It's a very nice control package when you want to close the loop around precise delivery of different fluids. The soft start, open and close. I've touched on this multiple times throughout this review here, but really, because of the eclipsing of the flow paths, you're able to deliver your sample into your environment as softly as you want. I've been in a lot of applications where any disturbance whatsoever is enough to cause the downstream sensors that you're utilizing in your circuit to be unstable. They freak out for a little bit, and it takes a few seconds for them to calm down. the soft start function out of the Eclipse eliminates that. You're able to control the delivery into your sensitive system. Whether you don't have to worry about damaging the samples, you don't have to worry about disturbing the downstream sensors. High resolution vacuum. Just was recently working on an application, and quite honestly, I was a little bit surprised on how well we were holding deep vacuum. I wasn't really given the whole details of the application, but what they are doing is they're pulling a vacuum in a chamber and then utilizing the Eclipse as a vacuum brake. But that vacuum brake is with different types of gases, both hostile and inert. You know, and I was really surprised because they were saying, okay, we really want to see better results out of the Eclipse. We're only able to hold 3 digits, so right at 3 to 4 digits out on pressure control in the vacuum state. So basically, they were going into deep vacuum. I was very happy that we were right there at that 4 decimal points out for maintaining vacuum pressure. But as soon as you start to open up the Eclipse, now the gases are being drawn into this, and they're using the sensors to monitor the chemical makeup, the percentages of makeup inside that chamber. The product line configuration. This is about as simple as a product line configuration can get. We have 2 configurations, a manifold mount and a zero dead volume fitting. We have a third option, but that third option is common to both, and that's the ENS or the encoder shaft option. A couple things I wanted to touch base on. When working with applications, we tend to go towards commonality, right? We find that we're working with a tremendous amount of similar applications, and in the case of the manifold mount, we find that we're working with a lot of oxygen or argon or nitrogen or just air applications. They want to have that finite flow, but they don't really care about the medium makeup. So we standardize on a black anodized aluminum manifold and an FKM gasket seal. Now, we're the manufacturers of this, so it's nothing for us to change that manifold out, change that gasket out to what's needed for the application. I could change this to stainless steel, PEEK, Teflon, it doesn't really matter. We can control that, but we need to hear back from you what you really want to do. But as far as a standard manifold mount version, black anodized aluminum, FKM gasket seal. If we're working with really sensitive fluids and I want to maintain my zero dead volume, fully flushable flow paths, my suggestion is we go into the zero dead volume phase. And I'll show you here an animation here that shows you how they go together. And then one last thing in regards to the Eclipse part numbers. If you go with the ENS option, it's an encoder shaft. We do not supply the encoder, but we'll give you the shaft so that you can actually put your motor on there and monitor position of Eclipse. But the neat thing about the encoder shaft is that, let's say you lose power and you're in a situation where you're controlling output gas and you don't really want it to keep flowing and you don't have power, you can't get it to do anything. Well, all you have to do is it looks like, are you good? Okay, here we go. Sorry about that. Gotta love live. So where I was at was on the encoder shaft. If I have a loss of power and I want to have a manual override, all I have to do is rotate that, and I can drive this back to a home position of no flow, or you can set it to a flow that is necessary with no power. Nice little manual override option there. Here's a video, a little animation of how the zero dead volume fittings go together. As you can see, we get rid of the FKM gasket seal. We're going to use the aluminum manifold or a manifold to help guide the zero dead volume fittings in. They'll make contact with the base ceramic plate. And as you can see by the cutaway here, as they make contact with the base, they provide no lips or no ledges and maintain a fully flushable flow path. So the top 10 features I want you to walk away from, at least thinking about some of them. The first one is that it's a stepper-driven proportional isolation valve. That's a nice thing to be able to say about a product. We're able to take your nasty little fluids and gases and give you very, very fine resolution control of flow. It is bidirectional. It doesn't matter whether you're putting the pressure to A or B ports. It's a very versatile product. It's rated for both gas and liquid. You know, we have some limitations because of ceramics, but ceramics as a whole is very inert and can work with just about 90% of all the things that we need to be able to control flow of. It is rated from vacuum to 30 PSI. We've worked with higher pressures. I've had it up to 40 and 50 PSI with no issues. However, the rating on this is vacuum through 30 PSI. If we need to consider higher pressures, we'll need to know the specifics about the application, and it might be just as simple as changing out the compression springs to afford that higher pressure. It's leak-free up to less than 0.05 SCCM. You know, we 100% test every valve that we manufacture here at Clippard, and when we say that it's less than 0.05 SCCM, we mean that because we're not going to pass the valve if it hits 0.05. We want it to be below that. So we're very comfortable in that when you get a valve, it will be leak-free to at least that level. It's fast response. Now, obviously, you know, I was able to go watch an episode of Andy Griffith while I was in the 1/16th microstep part of the video where, you know, it takes a while to go to fully open and fully back, especially if I can't control the speed. But if I'm in a position and I need to make steps in one direction or the other, it's very fast reaction time, less than 2 milliseconds. The cycle life of this is, we rated it less or greater than 1 million cycles, but you know, we haven't really been asked to actually have a different life cycle number for you. So if you need more, we'll test to that, but we'll need to have more specifics about the application, simply because we're rubbing the two surfaces together, and over time, you know, we need to understand what you're passing through there. What's the viscosity? You know, is there any kind of granular product inside this media, so on and so forth. All these things go into it, but we do rate this for greater than 1 million cycles. Its repeatability is better than or less than 0.5% of full travel. Our position resolution in full step mode is 600 thousandths of an inch incremental change. That's just in the full step mode. That's phenomenal resolution. And then our soft start. Talked about that multiple times throughout this presentation. The soft start, the way that we have the flow paths, how they're profiled, and you're able to create the eclipsing of the surfaces. It makes for a very nice delivery in your circuit. And that's all I really have for you in regards to the Eclipse. Apologize for the technical difficulties, but going live is definitely fun. But we're going to open it up to questions and answers at this point. And so thank you very much for your time.
Excellent. So thank you, Doug. We've got a bunch of questions that have been falling into the question box down there as we go. So we now have Tom that jumped in with us. And so let me just, I'll just read out a few questions. There's a couple questions around this. And Doug, you did talk about the time to go full scale. And so stepper motors in terms of how fast they can go and in terms of how we design the valve element. Tom, if you speak to, can you speak to the modes of the steps as well as the overall speed of the valve and how you have control over that?
Sure. So to start off, I want to say that when we do all of our testing in the factory, we do it at 1,000 steps per second. And that is at constant speed. So there's no accelerations involved in controlling the motor. Once we start introducing accelerations, you can ramp up to higher speeds. We were just kind of going for like a worst case scenario. In a full step mode, we're talking about roughly 1,000 steps going from closed to open. So you're looking at about 1 second there. You know, if you go into half step mode, you're still traveling at that speed of 1,000 steps per second, so it's going to take you twice as long. So you're looking at 2 seconds. As you get into the controls of a stepper motor, you can get really complicated and fancy, and people are doing a lot of really interesting things with stepper motors. So I'm confident that we can push that speed up a little bit, with some of those customizations. But like I said, our testing that we do in factory is sort of a worst case scenario, 1,000 steps per second at full step.
So 1,000 steps per second, but give me an idea, Tom, of the valve element and the resolution out of 1,000 steps in terms of to go fully open, fully closed in a full step. Roughly how fast is the valve?
So we're traveling 1,000 steps to go fully open. So it's going to take 1 second.
Great. I just want to make sure that's clear, because there's an element of how many steps you have, but that is, when we talk about that is the number of steps within the full scale resolution of the valve opening and closing.
Right, and as Doug mentioned earlier, when we start switching into the different microstep modes, that 1,000 steps, when you go into a 16 step, now turns into 18,000 steps. So you've got quite a lot. An increase in resolution there, and you're still controlling the valve in a per step mode, so you have to command it at a rate that's going to give you the appropriate speed that you're looking for there.
Excellent. And then Doug, real quick, there's a couple different questions on pressure and flow. So what is the max pressure, and at that pressure, what is the max flow of the valve?
As I said, we rated for 30 psi as the max supply pressure to the valve, and the calibration of the Eclipse currently is at 7 liters a minute at 30 psi.
Great. And Tom, if you wouldn't mind jumping into just the life cycle, the overall life of the valve and what our tests show, that'd be
sure.
Great.
So we've done life tests, over 1 million cycles. The main wear components in that valve are going to be the nut, and that's what the stepper motor is actually using to push the components back and forth. And then also there's an upper sled that we call it, that actually helps load the plates. So typically, somebody asked earlier about higher pressures. We can certainly accommodate specials. I believe, not sure exactly what the range would be. There's going to be a trade-off there. So when we add in stronger springs, what we end up doing is loading that nut and that sled a little bit more, so you have higher wear. So this doesn't necessarily mean failure. It just may mean that you're introducing maybe a little bit more hysteresis, or your performance is going to change over time. And with a stepper motor, that type of problem is really not that hard to overcome. Typically what we see OEMs doing is just running calibration curves. So over time you can just calibrate your valve and just basically map out your steps versus flow chart, and then use it as a reference when you're trying to control your media.
Gotcha. Thanks, Tom. I wish I could categorize these really a little bit better here, but I've got multiple questions around compatibility here. And so, Tom, if you go into the wetted material and the compatibility, and the questions range from what is the seal material, all the way to what about corrosive gases, ozone gas specifically is mentioned, ammonia. There's a few other questions in here about compatibility and wetted material. So if you'd address that.
Sure. Yeah, I saw the one about ozone, and no, unfortunately, we haven't tested with ozone. So the ceramic material is an aluminum oxide, and then also we have the Viton gasket in there that's wetted as well. Now, in order to fully eliminate the elastomer from the circuit or the flow path, you can switch to that zero dead volume adapter, and that will allow you to port directly to the ceramics. The material compatibility with the ceramics themselves. As Doug mentioned, it really depends on the concentration of the caustic media. You know, I look at hydrofluoric acid as being one of the worst offenders when it comes to the alumina. But there's other things like hydrochloric acid. Hydrochloric acid will, you know, run through the valve. What you end up getting is a rate at which it starts to, you know, break down the ceramic, and that's all dependent on concentration and temperature and things like that. So they're all very specific. You know, in general, I think we can broadly say that the ceramics are inert, and you're generally not going to have a problem with any material compatibility there.
Gotcha. So it's really that range of acids, and basically, if any engineers, scientists on the call here looking at that, what's it going to be compatible with? It's ultimately, we'll grab a compatibility chart for ceramics and really focus on that. That is the wetted material, and ultimately what you care about the most.
Right.
Dan gets the award for most questions here, so I want to clarify one of his questions where we started, and I might have been off on the timing. We may have answered this, but we talked about, again, that full scale resolution, 1,000 steps, right? So 1,000 steps is the full scale resolution. However, we can go down to a 16th step, so that so you can multiply that out, and what is that, 18,000? 18,000 steps. So the resolution of the controllable micro stepping is 18,000 steps, not just 1,000. If it's all about speed in your application, then you want the fastest performance, then it's 1,000 steps. So the trade-off there between speed and resolution is how you control the stepper motor in terms of micro stepping. So I hope that answers that.
Yeah. And you know, I want to also add in there that you know, I was talking earlier about, you know, getting fancy with your controls. You know, you can go ahead and drive to, you know, near your target flow, full step mode, and then kind of hone in with the 16 step and really, you know, fine tune that flow that you're looking for. So you can have a combination
jump to the closest possible in full scale, and then narrow down and yeah, very good. Very good. Yeah, there's a couple commercial questions on, you know, quantity, capacity, and the price. And let me just say that everything is available on Clippard.com in terms of the pricing through distribution for discounts and quantity discounting. And that's pretty straightforward there. We can quote standard product within minutes. And of course, we do a lot of customizations, manifolding, other things that we can get into you as well. So that is a general statement that I think just covered like 7 or 8 questions on my list here, but that's good. Let's jump into hysteresis real quick. One of the amazing things about this, which answers a few questions here, is the performance in hysteresis. So with proportional valves, you have magnetic hysteresis, which is a much bigger factor. It's 80–90% of the issue of hysteresis comes from magnetics. We eliminated that with the stepper motor and how we're operating this. There still is mechanical hysteresis, but Tom, why don't you talk to just, you know, roughly what that hysteresis is, and then another question on feedback, closing the loop with an encoder.
Sure. So in general, you know, as you mentioned, the hysteresis is purely mechanical in there. So we have tolerance stack ups, we have a little bit of play on the motor itself, and so what that ends up with is we're looking at about an average of about 30 steps, and that's in the full scale or full stepping mode, which turns out to be about 2.5% hysteresis over that full scale. As far as the repeatability of that, that's where I think you know, we really shine here, because you know, we may have that hysteresis, but as somebody, you know, asked in the questions here, you can totally you know, code that out of your controls. So if you know exactly what that number is, you just have to account for it when you're changing directions. So also with the encoder on there, you can map your curve, like I mentioned earlier, and then you know where your step position is, and you can go right to that step position and have the flow that you're looking for. So the feedback there is great. I think ideally, if you're going to run a closed loop system, probably the best way to do it is with some sort of downstream sense on the flow. I think that's probably going to be the most accurate. The encoder is great for that positional location, but to truly know where you are, you're probably going to want to have that flow feedback.
Excellent, excellent. In speaking to the stepper motor, Doug, why don't you take this one? And this is more about the unique characteristic of stepper motors in general. Now we're applying it to the Eclipse here. What happens if you have a power failure, power outage, or an issue with the control side? What are the characteristics around the Eclipse in what happens in a power outage situation?
Well, normally we deal with normally closed valves, so they just shut and there's no flow path. But in this particular case for the Eclipse, you lose power, it holds last known position. So it will hold that. So it's a nice option if you want to be able to have a low power flow control. You want to get to a particular position, it's flowing, and you pull power up, you're not generating any power to it. As I described in the part numbering configuration, if you had that issue and that problem is something that you need to override, then the encoder shaft option you could just manually override the position that it's at no power and take it home or move it to a position that's actually conducive to a no power scenario.
Great. So we've addressed the hysteresis characteristics. A couple of questions back on the example that you gave, Doug, in the application on vacuum. You talked about 4 decimal points in vacuum, a vacuum on that, but what was the unit of measure there? Was that torr or PSIA? What was that?
It was PSIA. Actually, I'm sorry. It was torr.
It was in torr. Okay.
Yeah.
Great. Thanks, Doug. Let's see here. Get the hysteresis one. We're set there. Tom, you're gonna love this one because I know we're in the middle of testing this, right? Particle generation.
Yep.
Puts you on the spot.
I can't tell you anything more than we are in the process of testing this. So
right.
We have a liquid test that we're running that we'll be sending out to a lab, and they'll be checking for the ceramic particles basically in the flow path. And we have obviously our control sample with no particles in there, and then we're cycling it, and we'll be testing that fluid as well.
Right.
Remains to be seen.
Yep. So Tom, this one just popped in, and this is more of a control question. This would be ideal for our controls group, Chris or Chuck, to be jumping on this one here. Without the encoder, which can be a big cost adder and obviously more complex in controlling it, but without the encoder, how do you ensure that you can get back to a home position?
Sure. So there are 2 positive stops in the valve, as Doug mentioned. So on one side, you have the face of the motor, and basically you can drive that nut into the face of the motor. And what happens when you do that is basically the stepper motor just kind of stalls out. And so as long as you run it far enough so that you hit that positive stop, you can then travel from there to your start position, and that's a repeatable number. We do give you a sort of ballpark figure to hit on that step position with the valve. It's part of the serial number. I say ballpark because your homing procedure may be slightly different. So the speed at which you're hitting the home stop and moving forward may vary that number a little bit. So, but once you establish that procedure for homing the valve, you'll find your initial flow pretty easily. There's also a positive stop on the other end if you want to run it that way. But again, both of those kind of keep the ceramic from running off of the lower ceramic plate and keep it from leaking.
Yeah, excellent. Good. Yeah, a couple more questions on controllability, and this is more for a controls expert here. You lose power, it stays in its state. Depending on the application, that can be good or bad. Is there any way to program it so that it would close, kind of fail close?
You know, we did that with the proportional electronic, where we actually, once power drops and it immediately goes to some number, to a threshold that we know there's an issue, that designing the electronics so that it actually, from that point, if it sees that, immediately sends it back home. That would be a special circuit board to accommodate that.
Yeah, with the stepper motor, obviously you have to have power for it to move, right? So it's going to stay wherever it is when the power shuts off. Now, if you have some sort of redundancy built in there, you could have it closed potentially. As Doug mentioned, there's the manual option. If you do have that encoder ready version, we could potentially do a custom that has a knob on the end of that encoder shaft, so that, you know, in the event of a emergency, you could turn that to a closed position.
Right, very good. A couple more here, and then we'll get to wrap this up here. Let's go back to a hysteresis question across the life of the product. Has there been any, or do we show any hysteresis increase once we get to, say, 1 million cycles?
So that test is ongoing. I imagine there probably will be, some, let's say, minor change in that hysteresis, and that's just because they are wear components. Again, that can be overcome with periodic mapping or curve generation.
Offsets in the program. Yeah.
Right.
Excellent. All right. Let's finish up with one more question, and Doug, I'll give this to you. I'm going to give you 2 questions here, Doug. The first one, they're both related. The first one is there any stiction like some needle valves can sometimes get? And then the second question is, what are the advantages, disadvantages of using this proportional valve over a stepper needle like the ScpV?
Well, first of all, the great thing about the Eclipse is that it's designed so that it has the soft start, it has the 0 dead volume flow path. So if I'm working with an Eclipse, the ScpV, that's not designed for that. It's a variable needle valve, and you're changing the position of a 3.5 degree needle through a 152,000 orifice. And yes, it's going to give you very good linear control flow, but it's the design of the Eclipse is more for the isolation aspects of it, the being able to do very, very fine resolution control of different gases and fluids. Basically, you still have a variable aperture type valve, but they're completely different in regards to how they work. The stiction, I've not encountered any stiction in our testing, so the answer is no, there's no stiction. But I mean, maybe Tom has encountered some during his testing.
We have more than enough force to break those ceramic plates free. If you've ever rung together a couple of gauge blocks or something like that, you'll note that if they sit there for a little while, they do become a little bit harder to move, and it's the same way with these ceramics. But our motor is more than strong enough to generate enough force to break that free.
Excellent. All right. So, gentlemen, I want to thank both Doug and Tom on the back end, making everything go. Rachel, for doing a great job today. I think this was informative, it was good. And again, for everyone who watched, if there's any need, any questions, by all means, please reach out, contact us, and we'd love to help you out on your next application. So thanks for watching.
Thanks, everybody.
All right, have a good day.